Professor?
Exam? No, I made that. Can I get a copy of the applications of derivative summary? Did he give you one?
No, I didn't get one.
She has it.
Is it from?
I'll give you one.
Yeah, she has it.
I got extras. Amber, that's a summary of like 4.1 to 4.3. That whole sheet.
I squeezed it in one sheet. A summary of 4.1 to 4.3. Got it all in one sheet. That was my goal.
Professor,
I gotta handwrite something. Oh, go ahead, Art.
can I go, actually, she and I were having a discussion, 4.2 number 7, the graph. I
Yeah, let's
mean,
do it.
yeah, I mean, it's kind of.
Mean value theorem?
No, I mean, we got it at 3.8, but we couldn't find the C. I mean, like, it's very confusing. I know there was, C has to the same kind of, what you say.
Oh, number 7? Yeah. 7 is where it's like they just gave this sketch, and we gotta, the only way we can do that problem is we use this really sharp pencil. What's the slope between the endpoints?
3.8.
So the slope is 3/8.
Mhm.
So then every time we're trying to estimate all the points where that really happens,
It's 3 tangents.
yeah, you'll draw that one tangent line, right?
Mhm.
And then we're just gonna use a sharp pencil to try to find where that slope would be just parallel.
Here's the one.
If you can tell, it's almost like we could just, we're really just estimating. So I didn't want you to get upset if you look in the back book and you're like, you said 1.2 and the back book said it actually go to 1.3. Because there's that puny sketch right there. And that means that even the thickness of the pencil lead, Art, you agree? You
Yeah.
throw it off a decimal point or two. So don't let that problem bug you. I signed it though, I love the concept that you can look at something and go, all right, how many times does it happen to discuss the mean value theorem? But that's it, like most important for me for that problem is just to recognize it happened 3 times, there's 3 C values, we can estimate where they are, but you don't have to hit it perfectly to like 1 decimal place or something.
We got,
That's all good, so where was the first one at? At x equal to what?
1, 2, 3, 4, 5, 6. One is x equal to 6.
All right.
One is at 1 and 2, 3, x equals to 3. Another one is at x equals to half. Or
Yeah, one was early, around half or so, like right at the beginning.
Mhm.
It had that little dip. That's good. I mean, just somewhere approximate of where the x values are. Do not think that you gotta be able to look at that sketch.
yeah, there's no way.
There's no way. There's gotta be more details. Maybe it should be larger so you can actually take, because all we're doing, we're taking our pencil lead and we're going, all right, straight lines. Because they didn't give us the equation of the curve.
Yeah.
That's it. That's what's good.
If you're gonna do any like review problem, could you do like a hyperbolic function problem?
Yeah. You want the hyperbolic function? Let's see. Keep in mind the derivative of hyperbolic sine is just
Cosine.
hyperbolic cosine. We put this h after the s, right?
Mhm.
Feel free to call it cosh. I don't know what you'd call that though. Sine hx. So I'd call that hyperbolic sine, but I call this cosh of x. Well, the derivative of sine hx, hyperbolic sine is cosine of x, cosh of x. And then the derivative of cosh is what?
Sine hx.
But not like SCSES where you and I did this. With trig functions, yikes. SCS. We did trig functions like that, remember this? Then we're saying with hyperbolic functions, it does that, doesn't it? It just keeps always positive.
What kind of question would you specifically ask?
With that one, it would be a chain rule problem, similar to the ones we did in class, to recall. Like I remember we did one problem if you recall this, I can make up a function, but just so you can, I wanna make sure you understand chain rule. Where we, there was a catenary,
Yeah.
remember that, between the two poles? And we had to find the slope at the right pole. It was like x equals 7. There was an equation given, but you and I knew, okay, we're just gonna take the slope and plug in a 7,
Yeah.
right? But, I mean, I'll make something up. It's just like, if you're given some function, let's say y equaled 40 sine h of x over 40 plus 22 minus 19. I'm just making this thing up, right? But here you got some hyperbolic function here with the hyperbolic sign. Let's find the derivative though. So differentiate. The 40 stays for the constant, right?
Mm-hmm.
Alright, what's that become?
Gosh.
Gosh, good, you're doing chain rule. I like this. When we do chain rule, that's G. We put all G back in. Alright, so let me put all G back in. I'm stuck, here's G. And then multiply G prime.
That should be
The
one.
derivative of where we call this part what? We call that G. Now be careful, it's not too bad. What's the derivative of a 1/40th x plus 22? The plus 22, to differentiate that, you get 0, right?
So
But a 1/40th x,
1/40th.
you just get 1/40th, don't you?
Mm-hmm.
Okay, good. So let's multiply 1/40th. Now what happened to this derivative? That just
0.
became what? 0. I'm going to multiply now the derivative of that. 1/40. Cool. And I just made this up. And now you go, okay. And if you want, see this 1/40th at the end? And with the beginning of this 40, we could what? They cancel. Let me write it again. X over 40 plus 22. Now, so that's, you differentiate it, great, that's what was key, I wanna make sure you can do that. And then second thing we did, I remember with the application problem, we had to find the slope at the right pole, it was like x equal to 7, so could you evaluate this slope at, I'm just gonna make up a value, x equal to 5. Okay, we just have to plug in a what? 5, but do you know how to do it on your calculator?
No, I don't.
Cool, I want to show you where the cost is. A lot of us go to the catalog. So I say that. I'll show you what catalog is. It's just, it's nice. That way you don't have to put in the original hyperbolic function. Okay, you got the calculator working? Boom, yeah. Second, 0, catalog. Let's get to the C's though. Where's the C? Right there? All right, boom. And we're looking for cosh x. Yep. But see, the key is, you don't even have to worry about the C. The key was, you want to get the catalog, which gives you the menu, the whole calculator. In this menu, it has to have the hyperbolic function somewhere. I just didn't feel like scrolling forever, so I was like, how can I get to the C's quickly? So I saw C right there, and I was like, thank you. I still gotta go down to what? Gosh. Oh, for hyperbolic sign, look, right there. Keep going, keep going, keep going, there it is. All right, now we gotta type in what? I said at 5 divide 40, and then plus 22, and you can evaluate. That work? Holy cow, that's huge. That's crazy. Cool. It's funny, we didn't go so heavy on that section. It's just, we're gonna know these. You may see these from time to time. Calc 2 course, there might be a little problem where all of a sudden a hyperbolic function comes up. They didn't allot a lot of time actually in our syllabus for it. They just want to make sure everyone hit on those. I'm like, okay, I get you. Make sure the students are aware of these, but don't go crazy with the inverse hyperbolic functions and stuff like that. If anybody saw that in the textbooks, you have to do those.
What about the formula? There's a formula for these, the y equals ex.
I think it's great to know those. You don't have to memorize them. I think it's great to be aware of that. Because a lot of students don't know that. They think these are like trig functions. They get in the calculator, it's like this, there's something going on where a lot, happens to a lot of students, they go, "Oh, those are the trig functions," or like, they're not even a part of, their relationship is just like trig functions, but they're not. Those are the actual functions, the e to the x plus the e to the negative x all over 2. It's good to know it, you don't have to memorize it. It's good to know that, so you're aware that this thing, this function right here came from another function. This right here. And it's e to the x. Is this the one with the plus or the minus? I don't even know.
Minus.
This is the one with the minus. So it's e to the x minus e to the
Negative.
x all over 2. And then the cosh has a what in the middle?
Plus.
Plus. So it's good to know, you don't have to memorize them, it's good to know that. You know? I'll tell you what, online students, sometimes they don't know the cosh and the hyperbolic sign are in that catalog. So they're typing things like this when they get evaluate like x equals 5 and stuff. They're plugging 5 into that. Cool. Alright, hey, any other? These are great questions. Anything else? Alright, hey, the last thing we left. I'll make sure at the end of class there'll be time if you have any questions. The last thing we left off on was this, it was an abstract topic. We had to actually look at a derivative graph, Amber. And this is what we did last class at the very end. And then we had to kind of think about what's going on with the original function. So it's abstract. There's not going to be any equation given to you. We're just going to go by the definition. So if you're like, I'm not aware of some of these, they're all on a sheet. These definitions for like, what does concave up mean? What does concave down mean? What's it mean for a function to be increasing or decreasing? It's all on here. So, you want to build another one?
Yeah.
All right, so and we're just going to build something. We'll build some derivative graph, and then we'll answer a bunch of questions about what's going on with that. Cool. All right. These are fun, but they're not so much fun if you're not seeing it. So just ask me questions if you can. It is kind of abstract just because you're not getting a function given to you. And you just got to go by the definitions. All right. So this is in 4.3. All right, here's an f prime graph. I always have a habit of writing the same exact thing I did the last time. I gotta make sure I didn't do it. So I'm gonna look, anybody has the picture of the last graph I did? I'm gonna change it up at that. Oh, thank you. All right, let's switch this thing up. I went down like that. Let's go down there. Let's pull this thing up somehow. Maybe that. Now I'm going to make up some x values, okay? That right there is x equal to -7. Right here, when this thing bottoms out, that's x equal to -4. Right there, that x-intercept, that's x equal to -2. And when this thing gets to the highest point right there, that's x equal to 1. This isn't drawing a scale, I'm just making up some x values. Right here, this is x equal to 5. Right there, that's x equal to 8. And then right over here, this is x equal to 11. On a test, when Professor Mestre builds a graph like this with software, if you can't tell where it got to its highest point, if you think it's like 1.2, I'm okay if you were, you know. I mean, I'll generate it with software if you like that. Looks like it's at 1.2. But I try to make them nice integers so you can answer these questions, okay? All right. Now, this is in 4.2. Now, where are the problems in the book that are kind of like this? You would see it right at the beginning. So at the first few questions, Stewart's textbook does that. He kind of hits on these concepts, right? Leave these out here in case someone wants an extra. Sometimes they have a student in another class and they give it to them. So we'll go through this. But what kind of questions did he ask? Well, in this problem, and this is what the author wrote. Using the given the graph, What interval is f increasing or decreasing? At what values of x does f have a local max or min? Alright? I'm talking about problems like number 5 and number 6 on page 297. So, this thing's like number 5, number 6 on page 297, and it's coming from 4.3. Okay, so let me just throw down a bunch of questions. Here we go. This is what graph again?
F prime.
And every one of my questions is about f. Every question is about f. All right. Now let's see. Let's find all x values. There could be more than one. But it could be 0. I want to find all x values at which f attains a maximum. What kind of max? How about relative max?
So that's the local, right?
That's right.
Yeah.
Thanks for bringing that up, Art. Sometimes they say local, sometimes they say relative, right? I'll put that in parentheses. Local. We'll put them here. If you don't feel like copying all these words, feel free to do the little, no, because I'm going to say the same thing, but right afterwards I'm going to say minimum, okay? At, if you like to use the at symbol, at which f attains a relative or local it could be more than one. What else are we going to do about it? Do you notice every question is about not f prime, but what?
Yes.
Fight the next question. Can you tell me the interval f is increasing? What interval is f increasing on? On what interval is f decreasing? We'll fill that in. And then I'm going to ask about concavity and points of inflection. That's what I like to do. Similar to this. All right. Let's see, I'll write it. Find all x values. At which f attains a point of inflection. Abbreviate a point of inflection. You can write POI, or some students like to write IP. I get the IPs a lot because that's what a student took calc before. They're like, that's what my calc teacher used to do. IP for inflection point. But a point of inflection. Point POI. More than one will put it. And then final intervals where f is concave up. And lastly, where is f concave down? Okay. So it's abstract because we don't have f. This wouldn't be hard at all, I think, for anybody. If they give us the f graph. What makes it abstract and a little challenging, maybe abstruse, is how abstruse meaning difficult to understand. This is f prime. So we really got to live by the definitions. One thing to note, everyone, do you have to sketch f in this problem? No. But some students like to try it. I see it all the time. They take their pencil and they start trying to draw this. So where is this graph above the x-axis? All the way up to what?
Negative
Negative 7. Then again from
Two.
negative 2 to 5. Then again from 5 to 11, right? That means the graph was increasing on that entire interval. That's what that means, Amber. Or anybody in here. It means f was increasing. F is going up. It's going up all the way up to -7. Then it's going up again from -2 to 5, and then again from what? 5 to 11. Because f prime means slope, and we're saying anything above the x-axis slope was positive. So sometimes the game, you're like, what's on the top? What's below? When was the graph going down, F? When was it decreasing? From -7 to -2, where else? After 11. So when I know this is a silly graph here, and I'll get your question in a second, but I know this is silly, but I'm just like, okay, this is what I know it happens. This is what F kind of does. It kind of goes, all right, it's going up, and then at -7, everyone, it reaches some highest point. Then it goes what? Then it goes down. I just want you to see this. It's like some graph went up. All right, now it's at -7. Then it goes down, and then at -2 it's at some low point, right? But when it doesn't do these straight lines, it would curve. But then it reaches a low point. Then what does it do from here all the way up to here?
Goes up.
It just keeps going up. It's gonna, the graph's gonna go up and 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 up. Let me get right over it. Right about 11. X equals 11 will be at some, and then this was at x equal to what? -2, and then what will it do again?
Go down.
Because it's underneath. Cool? Right, good.
You got it.
Oh, cool. And I know this is silly. You see my straight lines? It's kind of pathetic. You're like, it's not going to be straight lines. It's probably going to be curving and stuff. But just knowing the graph doing something like this, it behave in this manner, really what? Gives you an idea how to find at least these first few questions. You can crush through this one, this one, this one, and this one, knowing that. Do you see it? It was like a game. I took my arm, I was like, where was it on top? Okay, up to there, from there to there, there to there, and where was it below? Does that sound good? Alright, so now, can you see any local maxes? You might use this to help you figure it out. That's a what? Local max. Let me put it at x equal to negative what? -7. Anywhere else? So when you okay if I write x equals -7, then I'll write x equals what? Just like that. I'll list them like that. Because they said at what x values. They didn't say, they can't ask x, y values. I didn't give any y's. Right? You couldn't ask what's the y value. You didn't give it to us. All I gave were these x's. Does that make sense?
Yeah.
Now, hey, you know what some students do? This is over the years. Yeah, I've had some who they just memorize. They go, okay, when I look at an f prime graph, they know that if the graph ever does that from left to right, see how it did it here and here, they go, that's a max. There's a max occurring there. And they know if it ever did what? If it ever goes like that on the x-axis right here, that'll be a min. So I'm going to write that. And I always get a kick out of it. Some students like to know that. I put something like that at the bottom of my sheet. I actually included it on here. At the bottom right corner, I wrote that. If that helped anybody. I think it's more of this, though. I think it's more just conceptual, right? The graph's going up, graph's decreasing. Now it's increased, right? It increased from here to here, then the graph decreased. Does that help? So everyone, when I'm grading, I see stuff like this all the time. Sometimes I see really pretty graphs. Like the student actually took the time to really figure out the concavity and everything. Cool? But you don't have to. You don't have to. I want you to think you have to make the actual perfect graph. All right, where's the local min now?
Local means -2.
Someone, if you want to, there we go, right there. I mean, you want to memorize something like that, you can. Now, that means we can answer these. Where's it increasing?
-infinity to 7. -infinity to 7.
Oh, no, it's showing up there when you're like, it's increasing. Then it's decreasing. Then it's increasing, right?
Yeah.
So let's see, from x equals negative, what, infinity?
Yep.
All the way to x equal to
7.
-7. Boy, that's abstract, because you're looking at a picture where the thing's coming down. And you and I are saying, yeah, but f is increasing there. That's what I'm saying when I say this stuff's abstract. You're like, what? Yep, because it was above the x-axis. That means slope was positive. So I'm going to say, from -infinity to -7, let's get a union symbol ready. Because where else did he go up? Now, everyone, some teachers would take off like a point here, I'm nice. If someone wrote this, I go, they get it, they kinda get this, but you know what I'm gonna do at 5? I'm gonna break it up again. Because really at 5 it did what?
Decrease.
You see it actually hit a, right here, something's going on there. We're saying the slope was 0 there. So it was like increasing and then the slope was 0 at an instant. Right? This means slope. We're saying so slope of f at x equal to 5 actually equals 0.
How come it's not positive infinity? From 5 positive infinity.
Oh, I went from 5 to 11 because look at the end. It dipped down below again. So right after here, what did graph start doing? Because look, remember our game? Above or below? Above x-axis or below x-axis?
Oh, 'cause
It's
it-
below x-axis, you're like, it's decreasing.
So instead, if it was like just going up like an
Then you
arrow,
would've got it.
then it'd be
That's
positive.
exactly it.
Okay.
Isn't it funny? It's a game here where you and I are thinking, I'll write these words, then I'll erase it. It's like, when is the graph above this x-axis? And when is part of this graph below this x-axis? Because whenever it's above, it means f prime is positive. It means the graph's going like this. Whenever it's below, it means f prime is negative, which means the graph's going like that. And we're getting through like, oh, this abstract stuff won't get us. We got it. All right, man, we have filled out so much. Heck, when was it decreasing? So just check when it was below, Aaron, -7 to what?
2.
Negative
-2.
-2. Anywhere else? Ah, there we go. Kelly, thanks. Amber, there it is. 11 onward, it was below. So now I'll write that to me. Does everybody have that? Remember, I build this stuff with software when I make a test. And I'll try to mess around. It's kind of fun. I'm messing around with functions to put into some software program to make sure it has some x-intercepts and stuff. But sometimes this might be at like, you'll be like, is that -4? Is that -4.1? When it comes to answering some of these next questions, okay? I try to make them all integers. Feel free to use the closest integer. All right, now we're talking about points of inflection. This part's fun. Ellen, we go, what's the definition of point of inflection? Concavity changes. All right? That's what a concavity of f changes. Well, concavity is determined by second derivative. Right? We know that we can find any point of inflection if we can set second derivative equal to 0, or it does not exist, and the concavity changes. But this is first derivative. So all we gotta do is look for the hills on this thing. I'm serious. Tops and bottoms of hills, we're gonna find points of inflections on this thing. Like right there. Oh, that's a point of
Inflection.
You go, really? Yeah, because look, this is f prime. Then f double prime would change. Because f double prime is the slope of this funny thing. So that's why I'm saying it's right there. Where's another hill? Oh, right there. You got a point of f. I want to make sure I say of f, because I don't want you to think, is that a point of inflection of f prime? Boy, that's even more abstract, huh? We're not going there. Point of inflection of f. Here's another what? Point of inflection of f. Or right IP. Here's another one. 1, 2, 3, 4. When there were 4 points of inflection.
Even the 5?
Even the 5, even though it's on the x-axis, here's what's happening. F double prime is changing. F double prime is changing, because this is f prime. It changed, slope changes. Sounds funny though, because this is f prime, and I'm talking about f double prime, which would be the slope of this. Right?
F double prime is the slope.
Yeah, it would be the derivative of this.
Okay.
Does that make sense? But so it's wherever the hill, so it's going to be where? X equal to what?
-4,
Where else?
1, 5, and 8.
Now everyone, all we have to do to get these next two answers is dip between all those numbers. What's going on between these? Concave up, everyone, the definition. This is why definitions help. Concave up. F is concave up when second derivative is positive. Well, this is first derivative. So all I need to do is figure out when the slope was positive. I think I'll circle it this time. Okay? Yeah, right there. Yeah, right there. I'm circling. That's when the what? This thing was going up. So that means that double prime would be positive there. Derivative of this.
So when the slope of the F9 graph is positive?
Yes.
Wait, the double
You got it. That's exactly it, Josephine. Write it down. You go, why? Because this is F prime, and we're trying to look at when F double prime is positive.
So then that means that would be the concave, for concave up.
Yep, so let me tell you, from -4 to what? And it should be in between these numbers.
Point of it,
So -4 to 1, where else?
5 to 8.
And then you'll notice it's between these numbers right here. These numbers are going to fall in these answers here. And then this should be the complement of that. You know that word complement? You know, it's like,
Inverse opposite.
yeah, what's the complement? Everyone, is a 70% chance it's going to rain. In probability, what's the complement? We say the complement is 30% chance it's not going to rain. But it's like, all right, if that's -4 to 1 and 5 to 8, well, then where was it concave down? From -3 to -4, right? Yeah. Union. 1 to 5. Anything else? You nailed it. Holly, very good. Did I hear that?
What about 1 to 5?
Uh-oh, did I mess up?
No, I'm just not on the.
Yeah, do you agree? So it went down from 1 to 5.
Yeah.
From 1 to 5, right?
Oh, I didn't see you wrote that, sorry.
So right, you are exactly right. So -3 to -4, from 1 to 5, and from 8 to infinity.
Right.
F is concave down. Now, you know what's neat, Sarah? I've seen students draw this graph before. Now, you may like that. Some teachers like that. They like to get students into that. To me, I'm like, no, just explain you could if you wanted to. You could sit there and get your, be an artist. You know, what's graph that's concave up look like of F? Concave up means F's doing something like that, right? And concave down means the graph's what? So you really can improve this sloppy straight line graph I made. True? Like right here, do you agree the graph went concave down, then it went concave up? So what would that look like? Concave down would mean like, maybe the graph went what? Concave down, and then it changed to concave up. I'm trying to talk about what's going on like right there. Let me move it over. Like right here, if you really want to know, it's like some graph went concave down and then concave up. Well, this is what concave down means for F. This is what concave up means for F. So let me do that again. It's almost like the graph did what? It was like, oh, right here, it was like,
Concave down.
yeah. And then it had a slope of 0, and then it changed to what? Concave up. Right there. Still increasing, but it went, F went concave down and concave up. Point of inflection right in the middle. See? So I've seen students build clear just a pretty graph, you know, if you want to. Then they're like, can I get bonus for this? I got a really nice graph going on here. They really showed this whole design going through. Everyone okay with that? I know that's some abstract stuff, but not cool.
Can you
Not
do?
bad at all.
Could you do one more hit? That's cool.
Yeah, let's do another one now.
Yeah.
How about you all make it up? Does that work? Anybody want to come draw it? Just put part on top, part on the bottom. Hey, you want another one of these, right? All right, you're gonna make it. Do whatever you want. I don't care where you do it. Make it smooth too. Make it like a polynomial. And then, while she's making it, I'll go over here, find another eraser. Thanks, Amber. And I'll erase all these answers. I'll grab this. This will be fun. And we don't care if it's really simple. Do whatever you want. Do whatever you want. Make that thing smooth. I like it. Yeah! Holy cow. I love it. Perfect. That was great. I'll make up x values. I'll just put some x values. I do want to point out this graph right here is f prime. So listen, and this is f prime. Right there. Amber, that was great.
Thank you.
All right, let's see. What's that x value? Hey, I'm gonna let this thing just swing up forever. All right, that's x equal to -8, -6, -4, -3, -2, -1, that's 0. Not drawing a scale though, don't worry. Will that work? So -1, -2 right there, -3, -4, -6, -8. And when that's 1, that's 2, that's 4, that's 6, and that thing takes off. See, here you go. You might go, wait, that kind of bottomed out at 3.8 or 3.9. Oh, we'll just say 4. Right there. Take your timer when I know you got a lot of writing to do, because you got to put all that down. We're going to find all x values which f contains a relative or local max and a local min. And where's f increasing? And where's f decreasing? Find all x values which contains a point of inflection. Where's up concave up? I make this problem worth like 7 points on a test. My reasoning, I mean, I could have made it more than 10. I've seen some students, they love all of chapter 4. Some students, and they hate this. I mean, they love the optimization at the end. They love the application of Newton's method, which we're going to do later this week. They just don't like this. So that way, you know, someone will be like, all right, I hate this. And they get their, they can still score very well. Hey, remember the game, above or below. If it's above, the graph's what?
Increasing.
I'm already looking. Where's it above?
-4 to now, -2.
All the way to the -8? -4 to -2, I love it. Anywhere else?
0 to 2,
There you go. This is when f's increasing.
6 to infinity.
I almost missed the end. I got so tired when I was like, I must have hit them all. But Amber made a tough graph. It was good. Challenge. So f is decreasing when, what, -8 to -4? And from -2 to 0? And 2 to 6? All right, where are the maxes and mins? If you want to use this, you can. I don't know. Hey, Kayla, do you like these kind of things? I mean, some people like that.
I don't like that.
See, she doesn't. I kind of agree with it. It's more conceptual. They just memorize it. They just go, all right, whenever the graph went like that on the x-axis, right, across from the top, because that means the graph what? Conceptual is, it was increasing and then it was decreasing. This thing was going up, then it was going down. There it is. There's a relative max. There's another relative max. There's another relative max. Here, here, and there.
Oh, so relative max is basically if the graph is like this way you can count.
You bet, Art, I love it. And you know why? Here's you and I conceptual. We're like, yeah, because that means we describe graphs left to right, and we're always saying, all right, the graph was increasing and then decreasing.
Decreasing, okay.
It's a relative max. That's why. That's what's going on here on conceptually. percent of the graph was increasing and then it was decreasing. It's gotta be a relative max at those locations.
You drew a second graph for the other question, could you do the same one for this? Like,
Oh, yeah, you wanna try it? No, let's be sloppy, okay? Hey, let's just be sloppy, we'll just do straight lines, right? Let's talk about it. So remember, anything above means the graph was what? Going up. When anything below, the graph was what? Going down. Alright, here we go. And you go, where do I start? I can start anywhere. I can just start right here because I want to have enough room. Right? Alright, look, it's above. From here to here is above. So that means the graph did what? F went like this. F went up. Kind of sloppy, but now stop. Right there, stop. Now what did the graph do from here to here?
Went down.
Went down. Stop. I know it's sloppy, straight lines, but it's the idea. What did it do from here to here?
Went up.
Went up. Stop. Right there, it stops. It's going to go what?
Down.
Down. It looks like it'll go way further down. You can compare areas.
Mhm.
If there's more area underneath, that means it went further down. I mean, that's the idea. But hey, I'm just go down like this. Stop. Then what? Go up. Then what?
Go
From
down.
there to there, what?
So down.
Went down, stop. Sorry, I'm running into the other graph. And then what would it do?
Go up.
Go up. And you can look at that thing and you go, when was it increasing, when was it decreasing? And you'll see everything lines up. Then you can go back in and improve it with nice curves if you wanted to. Only if you wanted to. Alright, where are all the maxes?
But we can do it from the first derivative. Like if it is over the x axis, then that's increasing and
That's right.
yeah.
Then you can go back in and make it nice where it's concave up and concave down.
But for lazy people like us, we don't have to.
I know. It can frustrate you when someone said, hey, graph this thing. Now you're trying to do that, you go back, you start trying to really fancy it up with this stuff, right? Ooh, when was it concave up or concave down? And changing it, points of inflection.
So the only time we'd have to draw the first graph with the straight lines is if you wanted to see when it was increasing or decreasing.
That's right, and you don't have to.
You don't have to.
You don't have to.
When it's a positive.
For years, great question. I've graded these for years, and I've seen no work.
Okay.
I've seen no work from a student. And they have just gone,
Yeah,
bing, 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 bing,
that
bing,
makes
bing.
more sense to me than the.
And they're just sitting there going, oh, I got it. And they're just answering everything. So very good. Hey, so where's all the maxes? -8,
-2.
-2, and there's one more, where?
0.
Two.
+2. So where's all the mins?
Negative four.
-4,
Zero.
0,
Six.
and x equal to 6. If you want to put an x in front, you can. Here, an x equal. Just list the numbers. I want to make it easy for you so you can just list these numbers in. -8, -2, 2, -4, 0, and 6. Alright, now points of inflection. Do you remember where to look?
Yeah, at the
The hills, the humps. Look for the humps, right? There's one. Point of F. Point of F. I'm gonna write of F so someone didn't think I'm doing point of inflection of an F prime. I'm talking about the actual point of inflection of the original F graph. Poi, 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 poi. So there's a bunch. Boy, this graph is changing concavity all over the place, isn't it? But hey, she made a graph that's kind of like a sine, like a trig function. You got it at what, -6, -3, where else? -6, -3,
-1,
-1,
+1,
+1,
four.
and then 4. Thanks for your great graph. Now when we gotta talk about concave up, this is the last thing. And then concave down. Where do we look? Well, this is F prime graph. This concavity stuff, everyone? F double prime tells us about it. A graph is a function is concave up when its second derivative is positive, right? Here, F is concave up. Second derivative positive. A function is concave down. Oh, second derivative is what? So I like to circle. You ready? I'm gonna
Or also,
circle.
don't you have to look at between two POIs?
Yeah, it goes between poise. I love it, just between two POIs. So look, from here to here, concave up.
Up,
And then from here to here,
concave up.
concave up. I like the actual circle, so you can distinguish this from all my other writing.
And
Then again, from what?
4 to infinity, concave up.
Concave up. The opposite would be concave down. Has to be between the poise. Like he said, between the POIs. If you call them IPs. So here we go. From -6 to what? -3. Union. What was that? -1 to
One,
-1 to 1.
and 4 to infinity.
4 to infinity. Cool. Then concave down. Okay, -infinity all the way to that -6. Union. -3 to -1. Union.
1 to 4.
Wonderful. You're next. I'm trying to think of the craziest thing ever. Josephine, I could actually in here draw a straight line like that. But do you remember when there's a point like this? No JVCs, no corners or cups. So the derivative of that would be non-existent. Does that make sense? So I won't do that. Hey, did anybody have any other questions about problems from here? When we did first derivative, second derivative, concave up, concave down? Where you got answers when there's a function given. Was anyone give that? Awesome. Don't worry, everyone. I didn't want you to think like, oh, he's not going to do any more of those. We're going to get into 4.4 now. But sections 4.5 and 4.6, we don't have to do all the problems, but it's just another section that just go, okay. Can you put it all together now? You go, really? Yeah. Can you still again find where a function's concave up or concave down or where it's increase or decrease? And in those problems, Amber, they give you a formula. Okay, everyone? They give you formulas there. But let's now have some fun. Everyone, 4.4. What are we returning to? Limits. This is a cool rule. Now, if you go to 4.4, you all see a strange word at the top. Just look at the name.
L'Hopital,
L'Hopital.
Law Hospital.
Yeah. I'm gonna write it down. Seen it spelled a couple ways. It looks like a hospital. Everyone, this is for indeterminate form. Do you remember us talking about that before? Indeterminate form. What's one indeterminate form?
0 over 0.
That's one.
Infinity over infinity.
But there are others, and I just heard one. What was it?
Infinity over infinity.
And it might be infinity over negative infinity. It might be negative infinity over positive infinity, but I mean, these are just some examples of what? Indeterminate form. Are they listed in your textbook if you wanted to see them all? Yeah, you'll see a bunch of them. It's on page 302. You have to look now, but here's two key important what? Formats for indeterminate form. All right. Now, This is just another technique to help us to find limits. We already know a bunch, right? Actually, 3 ways. We've done it graphically, we've done it numerically, and we've done it algebraically, especially when we got an indeterminate form. We've been multiplying conjugates, simplifying fractions. Do you remember that on test 1?
Mm-hmm.
And you were all very good. This is where you get mad at me and you go, why didn't you show us this way? Because L'Hopital, this mathematician, when they came up with this, it's just a really neat technique to find limits of functions, especially when you get this indeterminate form to pop up. So let's start with something really basic. Something like that. Now I think you are going to look at this and know an easier way to do that. But I want, do you agree? Go ahead and substitute that 2 in there. You get 0 over 0?
Mm-hmm.
Okay. But what did we do back on test 1? Because it works and you can still do it.
You could factor it.
I heard it, you could factor it. Then you could cancel, right? So when you recall this, look, 0 over 0, we said that means you got to keep going. That means there could be a limit there, right? So what we did was we algebraically manipulated it. We would sit there and maybe do something like this, cancel these, then we took the 2 and we what?
Plugged it in.
Remember this? So now you get 2 plus 2, what's the answer?
4.
Is this okay with that? But that's not this lesson. I think you're going to like this section a lot better. Because back then, you and I had to be the master algebraic manipulator. We had to know about multiplying conjugates and doing common denominators, factoring, expanding things, right? L'Hopital's got it easy. He says this, right? If you get indeterminate form, right? Remember when he loved when you put an equal sign and put an H, just to say I'm now going to apply L'Hopital's rule. Don't do quotient rule. This is easier than quotient rule. Just differentiate the top and differentiate the bottom and plug it in again. No, you gotta be kidding. Yeah, that's simple.
2x
So I want you to differentiate x squared minus 4. What do you all get?
2x.
Yeah, I'm not talking about quotient rule or anything like that. No, just the top. It's like, okay, that'd be 2x. And how about the derivative of x minus 2?
1.
And then he goes, now substitute. What do you get?
4.
You may find this a lot easier. I thought someone in here was going to yell at me. This is where you go. Why didn't you show me this in test 1? I could have got all these problems. Well, we didn't learn derivatives really yet. We just got barely into it with the definition. You know? So, that's it. But let's see a whole slew of problems. If you got your textbook, and when he loaded this section. He's like, Cadoon, try all these limit problems. So let's do a bunch. Plus they're fun because what are we going to do for the next half hour before you leave today?
But professor,
We're just going to do a bunch of derivatives, right?
I got a question.
Oh, go ahead.
Now this L'Hopital's rule, right?
Right.
The thing that was like bothered me like during the first test was the sine of x over x when it goes to 0 is 1. That is the one he was doing.
Oh, can we do it now?
Yeah, in L'Hopital's rule is 1, but if I was trying to do it, I mean like it was always coming to 0.
No, it's hard the other way. It's
Yeah.
very hard the other way. Okay, let's show everyone that.
Okay.
This, yeah, you go, what's another way to do this? And boy, it is tough. It's even tough graphic. I mean, we got a nice graphing calculator, but then approach it just like numerically. I mean, and algebraically, what do we use? What are you going to put for sine of x over x?
Yeah.
So Art just came up with a good one. This came up earlier, and by far, this is going to be the easiest technique to hit it. No, seriously, you're going to say, oh, put that on the test. Right there, you're going to put that one on the test. Because that one, what's the sign of 0?
0.
And you get a 0 in the bottom. Don't we have an indeterminate form?
Mm-hmm.
These are indeterminate forms. So we'll just go, all right, I'm getting a 0 over 0, that's going to indeterminate form. Now what does L'Hopital like you to do?
H.
We put an equal sign, and let's just put a what?
H.
When we write that, you go, what are you doing? We're saying we're applying his rule. We're going to apply his rule and then write the substitute the number in there. Cool? What's their sign?
Cosine
Alright. What's their of x?
1.
You're like, are you kidding me? We're gonna be done. Be careful, cosine of 0 is not 0.
1.
The answer is 1. Now, and if you want to look at this, Art and I were talking about, okay, that's easy, but other ways, very challenging. If you got a graphing utility, you can make the graph and you can see that the limit's 1. But other than that, you know, if you say, what's an algebraic approach to do this? You and I know a bunch of trig identities. We'd still have to sit there and try to manipulate that thing to make it work. Cool. We know we got the squeeze theorem, that's sometimes handy. But boy, this really just makes limits a lot easier, huh? Hey, we're gonna do a bunch. You know in a final one I like to do like 30 multiple choice problems? Well, let's say 4 of them were limit questions. Doesn't that fair game? Doesn't that mean you can use any technique you've learned in a class? You could use L'Hopital's rule, right? I mean, you could do, the factoring. So sometimes there's 2 ways to do it. If I did that x squared minus 4 over x minus 2. But please be careful. I always say this. Please be careful. Don't be using L'Hopital and stuff like this. Right? I'm going to do L'Hopital. Sometimes people just automatically assume start doing L'Hopitals. And when you plug in 1 here on the top, what do you get?
1.
A 1. You plug in a 1 in the bottom.
0.
You get natural log of 1, which is 0. And your first step, you're getting 1 over what?
0.
This is not indeterminate form. That means non-existent limit. This is a two-sided limit question. Do you see that number right there? That is not indeterminate form. That means non-existent limit. And you say it's non-existent. Does not exist. Do you follow me? See, what's the danger of this? You're on the final, all of a sudden you start, oh, I'll take the derivative of x, I'll take the derivative of that, and you're going to get the wrong answer. Does that make sense? We're only going to do this when we have what?
Indeterminate.
These indeterminate forms.
So L'Hopital's form is only for indeterminate, right?
That's right.
L'Hopital.
Now, and I can make one like this, though. You want to see it? Now, what would be the answer to this? Limit as x approaches 1 of x over round of x. Does not what?
Exist.
Does not exist. DNE, non-existent. True? But I could make up one. It's easy to make one up. Try this one. Okay, there you go. I made this one up.
That's yeah, 0 over 0.
Aha, everyone, substitute the 1 in there. What do you get on top when you plug in a 1? 0. What's the natural log of 1?
0.
And you now say, alright, let's do L'Hopital's rule, right? Let's do Lopi. Alright, Lopi, put out what, an H?
Mm-hmm.
Just because it's cool. What's the H for it, that H? It just means we're applying what?
Derivative.
L'Hopital.
L'Hopital, yeah.
Plus, you might do this like in a differential equations class. That notation, your professor or instructor would understand it. Now, what's derivative of x minus 1? 1. Who knows the derivative of
1 over x.
Now, when we divide fractions, that looks kind of goofy to me. That's called a complex fraction. When you divide fractions, you multiply the... Yeah, they're reciprocals. Let me rewrite that.
So it becomes
This sometimes throws students off. They go, oh, I don't know what to do now. Well, you can plug it in now and get the answer, but sometimes it looks nicer if you just say what? This is also equal to, everyone, I'm just going to multiply the reciprocal. That's what?
X.
X over 1, isn't it? I just took that and went like that. But hey, I don't think you have to, because right now you can plug in a what? Jess, you can finish it up right now and get the answer. What's the limit of this function?
1.
1. Because we took this. So far, so good? Now let me go back to something we've done earlier in this class with the Horaces. Remember the Horaces? Remember the horizontal asymptotes? Remember those? Limits to infinity? Alright. We need to do a problem like this. So this was from test number 1. Okay?
Okay.
and you probably got it right, but I want you to apply L'Hopital's rule here if you can. So test one, you had to find this. The limit as x approaches to infinity of 3x squared minus 4 all over 2x squared plus 1. Now that was on test one. A lot of you figured this out by knowing it's a rational function, it has a horizontal asymptote. And you found the horizontal asymptote, you knew what the limit was. But now you know L'Hopital's rule. And what's 3 times an infinite value squared minus 4? Isn't that infinitely large? Think about that. 3 times an infinitely large number squared, that's infinitely large, minus 4, it's still infinitely large, like infinity. And over 2 times an infinitely large value.
Infinity.
I have to say that because infinity is not really a number, is it?
No.
It's some infinity. You're like 2 times infinity squared. Infinite, it's just humongous, right? Infinitely large, it's huge, plus 1. So I'm getting infinity over infinity. Indeterminate form. So what can I do?
L.
Let's do it 3x squared.
6x.
6x.
4x.
Now when I'm upset, but you can help me out with this. Now I go back to plug infinity, I'm getting 6 times infinity over 4 times infinity. I'm getting infinity over infinity again.
So divide by x.
What should I do?
Divide
Can I
by
apply Lopi again?
Yeah.
Yeah! Oh, and you can keep going with Lopi if you keep getting what? Isn't that cool? You might have problems where it happens 3 times in a row. Just keep crunching it down, right? Alright. Oh, I'm getting what? Infinity over infinity. 6 times infinity over 4 times infinity, infinity over infinity. Or an infinitely large number over an infinitely large number. So, what's that?
6/4.
That should be the answer.
2/3.
That was the answer on the test, but a lot of you
Yes.
reduced it to what?
Yeah.
Do you remember that?
Mhm.
I don't know, you might find it easier to just go, oh, well, the horizontal asymptote is 3/2, I'll just put that. When you're on your final, right? Amber, do you remember if you got that one?
Would you do after 6x over 4x? Would you do after?
Oh, I actually applied L'Hopital's rule a second time. Because I had infinity over infinity. I had 6 times an it's infinity, over 4 times an infinity. I had this again. And I can just do another round of Lopi.
Oh, then you got the 2.
Yeah. That,
Shouldn't you put the limit symbol out in front of 6x over 4x?
you can definitely do that. I think it's a great idea. If you always want to write that what? That limit expression each time. Because eventually we're going to do what? Substitute this value here. You got it. Great call. Is that okay with this? Alright. Alright, Owen, I'm going to try to stay to even numbers. I'll probably make some up along the way for the next 25 minutes. Does that sound cool? And then I'm going to end with my favorite, number 61. Because you go, whoa. And when number 61 is this. Do you remember this, John?
Mm-hmm.
I know, look. And remember a function like x to the 1 over x or x to an x. Remember these?
Mm-hmm.
They're kind of weird. Or x. We've only seen like 1 or 2 of these so far. Okay? So I'll end on that guy. Don't let it freak you out. That one with x to an x. You go, what the x to an x? How do you differentiate that? You might remember something we can do. Okay? Alright. Let's try some of these. I'll put this away. Limit. I'll try to keep you on your toes, so every once in a while I'll probably give you something that is an indeterminate form and just plug a number. Sound good? Like that. What do you do? Should I do L'Hopital's rule?
No,
What do we do?
it's pi over 4.
No, don't you just plug it in?
Yeah.
Alright, good. So always keep that in mind. Don't think everything's L'Hopital's rule, right? That's the bad part when you get a section like this. It seems like every problem, right there I just substitute 3. Pi over 3 plus 1 is pi over what?
4.
4. That's the answer. Alright, throw that one away. Try this one. Should I go to 0? Nah, I think I'll go to infinity. Can anyone read it? Can anyone read it?
Mm-hmm.
You do it. Just do it quick. Everyone, what do y'all think? Can I do Lopi?
Yes. Mm-hmm.
I agree. X plus x squared. Infinity plus infinity squared. Over 5 minus 3 times infinity squared. It sounds like I get an infinitely large number over a negative infinitely large number.
Mm-hmm.
So that means, everyone, look. That's also an indeterminate form. Yeah. Like something's approaching infinity, infinitely large, or something that's, infinitely large but negative. So what can I do? Some of you might already beat me and just did the horizontal asymptote on this. I'm going to keep going. What's the derivative? 1 plus
2x
2x.
minus 6x.
Now,
Again.
I get infinity over negative infinity again.
Mm-hmm.
What do I do?
Love it.
Do it again.
2 over negative 6,
What's the answer?
negative 1 third.
Now, if you write LH, will you still be okay, or do you have to write H for L'Hopital's?
Oh, you can write LH.
LH too.
I looked to his. I'm curious. Are you or anybody in here? Am I get a solution manual? Did you feel free to look through it? Artie, I don't know if you had a copy. If I have mine, I'll show it to you.
Okay.
He always writes the H. What's an H over the thing? Just almost like to talk about that thing. I guess just that.
Okay.
All right, here's a tough one. That's a tough one. Just remember, how do you deal with fractions again? When you get a complex fraction, you multiply the reciprocal of the. Because you all know ln of x is a 1 over x, and square root of x. What's the derivative of square root of x? You can remember that one, right? That's the one that comes up a lot. Oh, you're good. Did you just do it from memory? Josephine, very good. Oh, and first of all, let's just think about this. The square root of an infinitely large number. It's infinitely large. It's approaching infinity. Natural log. And when natural log is a very slow-moving graph, but it's also approaching what?
Infinity.
Infinity. Okay? So that's what we're trying to figure out. Is this, as this approaches infinity and this approaches infinity, is this overall expression approaching infinity, or is it maybe, going towards some number, converging to a value? So, infinity over infinity, we got indeterminate form. I can put my true. Good. Now what's the square root of x?
1 over 2 root x.
Zero root of x?
1 of x.
But now students get stuck. But you won't.
It's x over 2.
I want you to go ahead and reduce, make that look better. That's crazy looking. We want to improve that. So how do you deal with this?
You multiply the.
So I'm not going to put this equal to the h symbol over it, because right now I'm not applying L'Hopital's rule again. I'm just going to simplify this thing. I'm just going to put an equal sign and say this is equal to whatever 2 square root of x, put it times, and put what?
X.
Now this could be the hardest thing, because we're going back in the day to algebra. How do you simplify x over
So
square root of
f
x?
is root x root x.
That's a good way to look at it. And when you look at this, you want to break that down. Isn't x equal to a root x times a root x? Do y'all agree? So if you got to simplify this thing, isn't this just going to be this? Look. Square root x over 2.
Mm-hmm.
Is everyone okay with that? There's some ways to do this. That's x to a 1, that's x to a what? 1/2. But that's what's going on here. It's like one of these just what? canceled out. That's like a square root of x times. Everyone okay with that? You can look at it other ways. You can do a subtraction scale, like x to a first power minus x to a half power, right? Does everyone see that though? Sarah, that this over this is just the square root of x on the top. Yeah? So now, this is going to be an interesting answer. And I now get to substitute this. Oh my goodness, this thing is heading towards infinity. You bet. Everyone, this function is heading towards infinity. The square root of an infinity large number over 2 is getting what?
Towards infinity.
Infinity large. Just think of the graph. Square root of x, just what? Taking off, right? What's this answer?
Infinity.
You might have solved this at the beginning. Do you have knowledge of these two functions? Square root of x versus natural log of x, which is this slowly, put, rising graph. So these values, as you approach infinity, tend to what? Get this large difference, and that's why it's going towards infinity. Does that make sense? Very good.
I don't get why you don't have to do it again, because if you plug infinity in, it's.
It is
still
repeating.
infinity
If you do
I
it,
love it. I love it. She goes, why don't, we're not getting this. It may look like it. Look what you get. You get infinity over a 2.
large. So it's just infinity.
There you go. So we should talk about this. What if you get that? What does that mean mathematically?
infinity.
What if you got negative infinity over 2? What if you got, ready? Infinity over negative 2?
Same.
Negative infinity. Now I got a few others. It's going to happen in our next example. What if you got like 2 over infinity? I want you to think about it.
0.
2 over a million. 2 because these are limits. 2 over a trillion. 2 over quadrillion. What's it approaching?
0.
0. So when you see this, I want you to think that's roughly what? It's going to 0. The limit's going to be 0. Or what about this? Negative 2 over infinity.
0.
Or 2 over negative infinity. Again, I'm sorry, it's just going to be
0.
what? Because these are limits. We're saying if it's approaching that, if the top's like a 2, but the bottom's approaching infinity or an infinitely large number, you're like 2 over a million, 2 over a trillion, you're approaching 0. So do you see the differences in all those? That was good. So hey, Jess, on that note, look at my next problem. Don't take your time on this. It may look familiar, but it isn't. It's a little different. I want you to try it out. So again, Art, you might have a sense of this before you even start. That's good. That's good when you all have a numerical sense of what really is probably going to happen there. You know? I like when you all have knowledge of these functions. And you're like, you putt approach infinity. You know, in terms of height, this one grows more rapidly. So this is approaching infinity faster than this is. Do you follow me? You get a sense of what the answer would be. Alan, it's going infinity. That's going infinity. It'll be algebra. But Jess, go ahead.
If you did plug it in there, wouldn't you get the same answer? Because you would get, if you did the derivative again, you would get infinity.
Yeah, you're right. Sometimes that happens.
That's okay.
Yeah.
Okay.
The key is though, you do want to stop right there.
Because I feel like I'm not gonna remember that.
Oh, I think you will know. No, you'll know. You're like, listen, I'll keep going when I see indeterminate form. But the minute I don't have any more, I'm substituting my answer in to get the value. Cool. Don't worry. I know what you're hitting at. I know you go, I don't know if I'm going to know when to stop. I got one coming up for you. You're going to like it before you leave.
This one.
All right, you ready?
Mhm.
Let's do Lopi with their value of x.
1 over x.
What's that?
1 over 2 root x.
Oh, and I want you to multiply the reciprocal of the denominator so it looks better.
So it becomes 1 over root x.
Times 2 root x over 1.
Sorry, 2 over root x. Sorry.
There we go. Now we're going to simplify this. That's a root x over an x. That means 2 stays in top, but the bottom now just becomes what? Jess, I'll be honest, that seems to be the hardest thing for students, to be able to write this neatly. And they get all confused. They're like, I don't know what to do now. We're just gonna write it nice and clean. That's what that means. Now let's plug this in. We're gonna know what's happening. Here we go. There's no L'Hopital anymore. Think about this value. What's the limit? 2 over 100, 2 over 1,000, 2 over 1,000,000, 2 over 1,000,000,000. What is that approaching? 0. That's the answer. You might have saw it at the beginning though. When you see the denominator function approaching infinity much faster than the what? The top, you might sense it, and that's a good thing. Can anybody know of a very fast growing function out there? Very fast. EDX. That was good. So watch this. What's your hunch on this problem? It's very similar to this. What's your hunch? And then we'll do L'Hopi's. Then we'll do L'Hopital's. That's a very rapidly, right one? It's exponential growth, right? And I'm just going to do like something, x squared or prep. Who's approaching infinity faster?
Exponentially.
So what do you think is going to happen? It's going to be
0.
very similar to this. What do you think will happen?
0.
0? And if you flip it over, guess what it'll do? It'll go to infinity. That's when you have really good sense of this stuff. But everyone, you want to have fun and do L'Hopital's rule? But everyone, we're all saying this. We're like, we'll do L'Hopital's rule, but we get this. That's moving much quickly towards infinity than this guy, right? Just let you go, how do I know that? Everyone, am I going to calculator handy? What's 10 squared?
100.
100, right? Okay, what's e to the 10th?
Huge number.
What's e to the 10th?
22,000.
22,000. So at x equal to 10, this guy's way ahead of you, you follow me? So like you're getting much bigger quickly, right? Or quicker than the other one. And so you're like, yep, this thing's approaching
Is
0.
e the
Does
fastest
that make
function?
sense?
So when there's
And if
the
you flip this-
difference, when there's the difference in,
Yep. And the denominator has the faster one, right?
so when there's like a big difference, then that means that the
That's
answer
right.
is 0.
That's right. That's what we gotta look at. That's why, and the way you're looking at Samber, that's what L'Hopital was looking at. He's like, wait a minute, we don't know the answers because something might approach it quicker than the other. So everyone else, hey, can we do the math? We're all saying we should get 0 here, right? Well, let's see. I can do L'Hopital's rule. Let's start x squared.
2x.
Let's start EDX.
It is our x.
Now look at this, Jess, because this is what Jess was talking about. Jess, I can go again. Because infinity of infinity. What's your 2x? So I get to h, there's my h, I get 2. What's your v dx? Now, everyone, I have no more indeterminate form, it's now time to what? Substitute infinity. So what's 2 over an infinitely large number?
0.
Anyone on that note, I love to do this. Flip it upside down.
Is e the fastest function? No.
Great question. You ever seen this guy? I bet you say yes.
Oh, yeah.
Who knows factorial? Is there something out there that can beat factorial? What was e to the 10th? I forgot. All right, what's 10 factorial? Do you know where the button is? Go to math, PRB. Someone's gonna tell me it's huge. It's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1.
3.6288 e to the 6.
And what does that mean? Scientific notation, it's huge.
Oh,
Right? This is my favorite. What calculator you got?
Casio. It's regular.
Does your Casio do 70 factorial? Or is it too big?
Let me see.
Sometimes when the factorial is just too big.
Too big.
Calculator. It's too big?
Yeah.
Thanks. He's saying the TI-84 can't even do 70 factorial. Now if you're like, I've never seen a factorial before. If anybody in here, I want to tell you what a factorial is. 5 factorial looks like an exclamation point. It's 5 times 4 times 3 times 2 times 1, which is like 120. What's 4 factorial? 4 times 3 times 2 times 1, which is just what? 24? Okay, but this explodes very rapidly. You saw what happens at 10 factorial. That thing was gigantic. He says a calculator won't even do 70 factorial, it's too what? It's too big. So, all right, I'm going to write a limit on the problem. I don't put this on the test, but I want to see if you can get this. Art, do you know this answer? I got e to the x up there, that's a fast growing but I've got this guy in the bottom.
Oh, then, that should be 0.
Yeah. If anybody's curious, don't worry, I don't think you'll see that factorial symbol anywhere in this section. You'll start seeing it in Calc 2. Might as well give you a head start on it, right? Get used to it, right? And then you go, this is my favorite. You go, well, is there anything that can beat factorial? And you go, yep. How about that guy?
Huh.
This is fun. You go, all right, if you beat that, anybody can beat that guy? How about x to the x? And at 2, it's 2 to the 2. At 3, it's 3 to the 3, right? What's going on at 10? 10 to the 10th power. What's going on at 100? 100, so that thing's even
What
blowing
about-
that thing out of the water.
What about x to the x factorial?
Oh my gosh, see? This is not even me and him. We can go on and on and on. Keep getting something to just approach infinity more. Or you're like, how about this? The x to the what? You know? We're like, alright, that's enough. That's enough, right? It's fun though. It's fun. Alright, Owen, try this guy. Now, if you already know the answer, I'm very proud of you. Seriously, it means you have good number sense. You try that? If you're like, I know what this is.
Yeah.
That's pretty darn good. I mean, you know what it is, and you're that confident in your math skill. Please feel free to put that answer down. But it's coming out of this section, so it's like let's practice Slippy Tow's rule. But I'm serious on the test. Sarah, if you put the answer down and I didn't see any work, I'm okay. Right? It shows you have really good number sense. You understand limits. This guy's blowing this thing out of the water as you approach what? Infinity. Well, first of all, I can apply L'Hopital's rule, so I'm going to show how it works. What's derivative of 2x? Is that right?
Mhm. No, 2e to the very left.
All right, chain rule. You know it. It just comes up so often. What's derivative of 2x? Either 2x times up.
2e to the 2x.
What's derivative of x cubed? Just 3x squared, right?
Mhm.
Jess, I get infinity over infinity again. So now what's derivative of that?
4,
E to the 2x.
6,
Oh, goodness gracious. I get what?
8.
Infinity over infinity again? It's almost like Jess, I keep going until I get a constant somewhere, huh?
So there's not an x on it.
I like that. Yeah, you're right. That's a good eye. Because every time there's an x, you're plugging this in, you're getting infinity on one of the ports. What's that derivative? 8. But when I've seen people on tests do this. No, I mean, they did all this great work, I'm telling you. And I'm like, gosh, that just did nothing for them. You might have saw it at the beginning. What's the answer?
Infinity.
Yes, I love that. Because now you plug infinity, you're like, an infinitely large number over 6 is positive infinity. Right? What's some other tricks you can do? Especially in a multiple choice exam for a final. What's some other tricks? You know what you can do? I'm just going to see what e to the 2 times 100 is over 100 cubed. And just see if the number is like humongous or something. That means it's heading toward infinity. Kill it.
Is our whole final like multiple choice?
Nah, that wouldn't be nice. You may hate this stuff. So I like to do both. Do like some free response questions where you get the free response is good for like, remember related rates? Remember that? It's good to have one where you gotta, here comes the boat, what else do we do? The ladder falling and stuff like that, or maybe like a max min problem like we did earlier. Sound good? I'll do some more of that. Remember last Thursday? We didn't do it so much today because I wanted to get into this rule. From last Thursday when we go, we gotta find the actual relative maximum. We did the first derivative test. One of those problems. I'd say, find the relative maximums for this problem.
Oh, okay.
Does that make sense? Hey, cool. Everyone, just a couple more, okay? Try this. Just throw people off. Something about negative exponents drives students crazy.
So that's infinity.
I want you to take care of that daggone negative exponent right away. What does e to the negative x mean?
1 over e to the power x.
Excellent. e to the negative x means 1 over e dx. Can we write it like that first?
Mhm.
See, L'Hopital's rule is great when you got this fraction going on. That's not a fraction. Boy, it'd be nice if I could pull L'Hopital's rule. We're saying, yeah, just pull this where? So I'm just going to write, not an h yet, just rewrite this. Then I think we can do L'Hopital's rule, unless you already know what the answer is by just looking at this. Anybody already know who's growing at infinity faster?
E, denominator,
Do you have a sense of the answer?
so 0.
Gosh, I love it. Well, that's going to help you out. You'll find that very handy, not only in the next test, but the final. That means you get good sense of limits. Seriously. You're like, let's go in 0. But I'll crunch through all of Lopi, okay? It's going to take me about 4 steps, though, because what's derivative x to the 4th?
4x cubed.
Jess, I still got variables. So e to the x, e to the x. Do it again, I get what? Still got variables. I still got variables.
24x.
Finally, I get 24 over e to the x. What's 24 of an infinitely large number?
0.
You wouldn't have to show all that work. Evan, I didn't finish this section. Okay? We're going to do more of this tomorrow. But can I do that dude I was talking about? Can I do the x over 1x? Can I do it now? We're going to keep doing these. I want to make sure, you might be like, I got this stuff down. And we know what always worries me? When you're on the test and I throw this at you in a problem, and a student misses chain rule, right? So tomorrow I'm going to start with a couple more of these. What's the derivative of tan of 4x?
Secant square 4x 4.
Times a
4.
right. Cool. So I'll throw some more at you at this. And you might come in tomorrow and go, can you number 55 from 4.4 or something? You might have me do a problem from 4.3. But I wanted to end today with number 61. All right.
61.
This is bizarre looking. You know why? It's one of these guys. Something like that. We've only seen like one of these before. We did something called logarithmic differentiation. Do you remember that?
Mm-hmm.
And we're going to do something very similar. It's been a while. It was in this section where we learned implicit differentiation. I know. And it was something like this. So you might be looking at this going, I can't remember when we did this guy. We're going to do number 61, Josephine, and this is what it says. Hey, does anybody want the page number?
308.
Oh, thanks, Art.
No problem.
We're going to end on this guy. X goes to infinity of x to the...
1 over x.
Now, the author talks about more indeterminate forms of this sort. If you want to memorize it, everyone, you would see this on page 306. The author calls it, ready? Indeterminate powers.
Mm-hmm.
If anybody wants to look at it, he calls it. So if you want to go, I want to memorize all the indeterminate powers. In this case, everyone, if you substitute infinity, what do you get? X to a what? X to a 1 over infinity. Now you might say, well, that's approaching 0,
Mm-hmm.
but that's approaching also what?
Infinity.
Infinity. So this is why it's indeterminate. How fast is this approaching what? 0, as this is approaching infinity, this is what we call an indeterminate form. Okay? So you go, well, how the heck are we going to play with this? How are we going to play with this? We're going to use a trick like we did before. You know what helps? Is when we can somehow turn this into a log. Because with logarithms, there's a cool property of logs. Like if I had this, I went in math, natural log of 5 squared, I can do something with that too.
Bring the 2 in the front.
I can move it to the front. And so you and I, this is what's bugging me. There's a variable up in the air in the exponent. So this is what we're going to do. We're going to start out and do this. Let's say, now whenever we do this at the beginning, we got to come back to this at the very, very, very end, okay? Let's say we actually had to do this. The natural log of x to the 1. And find the limit as x approaches infinity. Okay? And you're like, Professor Muster, what are you doing? You're changing the problem. Don't worry, I'll come back to this at the end. But I'm going to look at this, the natural log of x to the what?
1 over x.
All I did was throw in what at the beginning. Can you do that? Yeah, as long as at the very, very, very end, I'll come back to it. Okay? So let's make a little reminder. Don't forget. Don't forget when we're done to come back to it. Come back, okay? Don't forget we're going to come back to it. You go, why did I do this? I think you all know. What can I now do with this thing?
Bring it to the front.
Right in front. And then we can apply this in it. Let's check it out. So when I do that, x, 1 over x times what?
Natural log of x.
What's another way to write that? Ln of x over x. Let me write it down. So this is the problem you and I now have. Well, this is cool. That's approaching infinity. That's approaching infinity. This is going to be easy. Let's apply L'Hopital's right now. So I'll put my equals, I'll put my h there. Would you differentiate this? And just like you said, Ben, then I can put that limb down again, right? Ben was pointing this out. He goes, every time you do L'Hopital's, you really should write this every time. Did you notice I wasn't, though, all class? Because I don't mind when students don't do it either. As long as you know to always what? Substitute that number at the end. Now, what's the derivative out of x?
1 over x.
What's the derivative of x? Oh. So let me write this again. What's the limit as x approaches infinity? Whatever x. Whatever a million, whatever a trillion,
Zero.
whatever quadrillion, that's approaching what?
0.
But, before you think this is the answer, and remember we go, that's it, that's the answer to the problem. Don't forget something. What did we do at the beginning?
Then infinity.
Hold up. What did we insert at the very beginning?
Let's.
An ln. So we got to reverse that. And you go, what reverses it?
Oh, so ln of 0.
Who's
so
his inverse buddy?
1.
Who's his inverse buddy? E. So did you know in math, e to the ln of blah is just what? I always forget how to spell blah. How do you spell blah?
BLAH is
Okay.
equals to E.
Is that right? All right. What's e to the ln of blah?
E. Blasters it.
It's just blah.
Uh-huh.
All right. So can I get it? What's e to the ln of 2? 2. What's e to the ln of amber? Amber. Right. This is what we're saying. E to the ln of x, x. E to the ln of y is y. So you and I did this at the beginning, right?
Uh-huh.
We threw this ln, so now we got to reverse that. Well, we know that e to the ln of x to the 1 over x will just be the
1 over.
original function. So for our last final step, so we don't forget, and we didn't, come back, what was this number?
0.
I need you to put e to that number. That will be your answer. This is my last step. This is what you always do. You go e to the, whatever you just got here. And you go, why? Because e to an ln of what? Of this puts it back to this. So what is the answer to this problem?
1.
1.
It's 1. I didn't forget. So this is what you do. You go, okay, if I ever want to do this like concept, just remember at the end, e to whatever you got, right?
Couldn't you tell it would be 1 though, since the exponent is approaching 0?
You know, that's good. You, once again, you got that number sense. I like when you can see that stuff. You know, from the beginning. You have knowledge, you can see stuff in the math problem. So very good. Excellent. Excellent job. Hey everyone, great job with this. Like I said, we're not done with 4-4. I want to come back tomorrow and hit with you a few more, okay? Have a great day.